see here. Looks like YouTube is up. Just waiting for Twitch. All right, sweet, we're online. So yeah, tonight was just going to go through this paper that popped up a couple weeks ago called Divergent Reflections Around the Photon Sphere of a Black Hole. So I'm not super familiar with exactly what this paper is about. I think it is basically something about this thing called the holographic principle, which is an idea in physics that kind of came out of string theory that suggests that the sort of physics inside of, I guess in this case, the universe, is really described by the state on the boundary. So you like the physics that's happening in like 4D space is like somehow encoded on the 3D boundary or something like that. Don't quote me on that bit. But yeah, so maybe this paper will have some interesting ideas related to that, and kind of interested to dive in. So let's give it a shot. All right, so from any location outside the event horizon of a black hole, there are an infinite number of trajectories for light to an observer. Each of these paths differ in the number of orbits. Sorry, one sec. How do I turn this off? There we go. Sorry about that. So each of these paths differ in the number of orbits revolved around the black hole and in their proximity to the last photon orbit. With simple numerical and perturbed analytical solutions, the Null Geodesic equation of the Schwarzschild black hole, we will reaffirm how each additional orbit is a factor of e to the 2 pi closer to the black hole's optical edge. Consequently, the surface of the black hole and any light will be mirrored, and any background light will be mirrored infinitely in exponentially thinner slices around the last photon orbit. Furthermore, the introduced formalism proves how the entire trajectories of light in the strong field limit is prescribed by a diverging and converging exponential. Lastly, the existence of the exponential family is generalized to the equation to the equatorial plane of the Kerr black hole with exponentials dependence on spin derived. What does this say again? Lastly, the existence of the exponential family is generalized to the equatorial plane of the Kerr black hole with exponentials dependence on spin derived. Okay. Thereby proving that the distance between subsequent images increases and decreases for respectively retrograde and prograde images. In the limit of an extremely rotating Kerr black hole, no logarithmic divergence exists for prograde trajectories. All right, so let's see if we can break this down a little bit better. So these first two sentences, they're just saying that, like, I think I saw a kind of picture of something like this. Was there another picture I saw? I guess this one up here is the main one. Yeah, I guess the basic idea is just that they're saying that, like, if light is going to travel from the black hole to you, I'm assuming this is light emitted from the black hole via, like, Hawking radiation, and not just light that, like, just barely doesn't fall in. But saying that, it can go from the black hole to any point, and there's, I guess, a allowed trajectory for it to go around the black hole any number of times prior to getting out and escaping and going to that point over there. So that's the first two sentences. With simple numerical and perturbed analytical solutions to the null geodesic equation, we reaffirm how each is a factor e to the 2 pi closer to the black hole's optical edge. So I guess this is saying that if you just study the solution of, so in general relativity, you have this equation that tells you how light or anything will move inside of a black hole, or sorry, inside of space, given the geometry of that space-time. So the geometry comes from understanding like the distribution of matter and energy in your space-time, and there's this equation that you solve that tells you, okay, if I know the distribution of matter and energy, then what does the geometry of space-time look like? So when you have a black hole, a perfectly spherically symmetric black hole, that's called the Schwarzschild black hole, and it has a well-defined solution. It's one of the easier problems in general relativity. So I guess they're saying if you look at the solutions there, you can see that there are these null geodesics. So light travels along what's called a null geodesic. It just means that the time that the light experiences as it's traveling is 0. We reaffirm how so I guess they're saying each of these orbits is e to the 2 pi closer to the black hole's optical edge. Okay, so hopefully we'll see how this actually comes about. Consequently, the surface of the black hole and any background light will be mirrored infinitely in exponentially thinner slices around the last photon orbit. The surface of the black hole and any background light will be mirrored infinitely in exponentially thinner slices around the last photon orbit. Okay, hopefully we'll get a better idea of what this really means. I'm not sure what they mean by mirrored here. But okay. Furthermore, the introduced formalism proves how the entire trajectories of light in the strong field limit is prescribed by diverging and converging exponential. So this is saying something about the entire trajectories. I'm not sure what entire, if entire has some special meaning here. Strong field limit means probably very close to the black hole. By diverging and converging exponential. I'm guessing this is talking about there's different paths the light can take either into or out of the black hole, presumably. Lastly, the existence of the exponential family is generalized to the equatorial plane of curved black hole with exponential dependence on spin derived. So curved black hole is a spinning black hole. And it looks like they're going to solve this, or they're going to look at the problem as well for a spinning black hole, at least on the equatorial plane. So plane that passes through the center of the black hole. That it's and normal to its spin. Thereby providing distance between subsequent images increases and decreases respectively for retrograde and prograde images. In the limit of an extremely rotating curved black hole, no logarithmic divergence exists for prograde trajectories. Okay, let's just get into the paper. So here's the introduction. Black holes are famously objects where, actually, let me quickly check the volume on this. I hadn't actually been paying attention to that. Make sure that the audio is all right. Let's see. Sounds okay. Maybe a little bit louder. All right. So, black holes are famously objects where the spatial paths of light are drastically bent by the curvature of spacetime. While light itself cannot escape the central mass at the event horizon, at further distances, light may orbit the black hole. In the generic case of non-rotating and electrically neutral black hole, i.e. Schwarzschild black hole, the event horizon is located at a radial coordinate 2g m over c squared, where g is this constant, m is the mass of the black hole, c is speed of light. While photons may follow unstable circular orbits at 3/2 the Schwarzschild radius, which is called the photon sphere or the last photon orbit. Okay, interesting. So I'm not sure why photons can't rotate. Seems like photons can orbit exactly at this distance if you have a Schwarzschild black hole. So that's interesting. And I guess this is called the photon sphere. Any photon orbiting below this distance will fall into the black hole, while light that remains further away will spiral out towards infinity. So we'll escape the black hole. I mean, it's not inside the black hole, but it'll shoot off. However, depending on the photon's proximity to the last photon orbit, it may complete several orbits before spiraling into the event horizon or outward towards infinity. As we approach the limit where the photon graze the exact critical orbit radius, the photon will orbit an infinite number of times. So it sounds like there's only one stable orbit, which is exactly at this 3/2 this Schwarzschild radius. Inversely, from the perspective of an observer at infinity, this implies that light from any point, from the event horizon to the background, from the perspective of an observer at infinity, this implies that light from any point may orbit the black hole an arbitrary number of times. Why is this conversely? As we approach the limit where the photons graze the critical orbit, they'll go an infinite number of times. Inversely, from the perspective of an observer at infinity, this implies light from any point may orbit the black hole an arbitrary number of times. Okay, I'm not sure. This sentence confuses me. For each of these paths, the light will reach the observer slightly closer to the edge of the black hole's shadow. Therefore, the observer will see the entire surface of the event horizon and the entire universe repeating infinitely near the edges of the black hole. Therefore, the observer will see the entire surface of the event horizon and the entire universe repeating infinitely near the edges of the black hole. This infinite mapping has been extensively studied with deflection angle diverging logarithmically in the strong field limit. Okay, I'm going to give this paragraph one more try here. As we approach the limit where the photons graze the exact critical orbital radius, the photon will orbit an infinite number of times. So this sounds fine. In the contrary, if you're really far away from the black hole, knowing that the photon can go around the black hole an infinite number of times at the critical radius implies that light that comes from any point may orbit the black hole an arbitrary number of times. Does this just mean because you're like so far away that there's some sort of resolution thing going on here? Okay. So let's just say I buy this, that when you're really far away for some reason, it seems like light from any point can go around the black hole an infinite number of times. For each of these paths, the light will reach the observer slightly closer to the edge of the black hole's shadow. Okay, yeah, I don't totally understand this. But okay, apparently this is well studied or something, according to them. Let's keep going. However, we present a methodology that differs from previous research by reformulating the trajectory of light in terms of second-order differential equation and quantifying its linear stability. In these simulated orbits, we investigate, or in a paper called Simulated Orbits, I guess, we investigate how small deviations away from the optical edge of a black hole will behave with a ray tracing algorithm. We supplement with an analytical derivation and linear stability. In both the numerical and analytical case, we show that small perturbations grow exponentially. Inversely, each additional orbit will be mapped to an exponentially thinner ring, each with subsequent imaging factor e to the 2 pi thinner. Ultimately, this paper investigates a well-known problem from a new analytical perspective, suggesting not only the deflection angle, but the entire trajectories of light near the photon sphere are prescribed by two dueling exponential functions. Crucially, this approach is generalizable to any spherically symmetric black hole, or even the equatorial plane of a spinning black hole. Any spherically symmetric. Okay, so kind of what I understand from this is that for some reason, if you're far away from a black hole, any light that like goes somewhere near it before it gets to you can seem to like get caught up in the black hole and rotate around it some number of times. And since that's the case, you can maybe catch light that like from any arbitrary point in the past that has been like spinning around the black hole for some amount of time before it gets to you. So that's what they mean, I guess, by you can see the entire history. And apparently this is a well-known thing that was studied some other way, and now they have a new way to study it. And their new way of studying it, it's not going to work only for these non-charged, non-spinning black holes, these Schwarzschild black holes, but also to Kerr black holes, which are these rotating ones, at least if you're interested in only looking at this equatorial plane. Okay, so crucially, this approach is generalizable to any spherically symmetric black hole, like I said, even in the equatorial plane. In generalization to Kerr metrics, the exponential dependence on spin is derived and illustrated. Here it is proved for the first time that the spatial frequency of prograde and retrograde images will retrospectively increase and decrease from the Schwarzschild case. So I actually, it's kind of embarrassing, don't know what these words mean. I think it's like one is coming towards you, one's going away or something. Proceeding. Okay. Spinning in the direction or against the direction of its orbit. All right, so analytical setup. The Schwarzschild metric has the form in units with the speed of light c equals 1 of this thing. So you basically just have this kind of time dilation term, and then this is in spherical coordinates. You have another term here for the dr, and standard r squared d theta, r squared sine theta d phi. So this is how you measure distances in that geometry, where rs again is the Schwarzschild radius. So if you move basically a tiny bit, or if you wanted the distance between two events that are like pretty close to each other in the space-time, the space-time distance is given by this equation, where you need like the phi coordinate, the theta coordinate, the r coordinate, and the time coordinate for each of those two events. Okay. So simulated rays of light satisfying equation 3. Is equation 3? No. So anyway, so this is our Schwarzschild metric. Without loss of generality, we can set the orbital plane of light to theta equals pi over 2. Introducing two conserved quantities, angular momentum and energy, we can, for a massless particle, reduce the equation for trajectory of light to dr over d phi squared. The dr d phi squared is minus 1 over Schwarzschild radius over r times r squared plus r to the fourth over b squared, where b is a ratio of the photon's angular momentum to energy. Okay. So they're just saying we're going to sort of reduce this problem by just supposing that whatever plane, so if something's orbiting, it's always going to be orbiting in a plane. So we're going to say whatever that plane is going to happen to be, we're just going to call that angle phi, that angle theta is going to be pi over 2. That's just how we're going to define that angle. Which lets us turn this into 1. And then I'm not really sure where the dt term goes. But okay. So for whatever reason, you can reduce this equation down to here when you set the light, or when you call the plane the light's rotating around pi over 2. Rewritten differential with phi is only applicable if there is angular evolution, so equation 2 does not apply in the limiting trivial case of light moving radially towards or away from the black hole. Okay, so it's saying this only is satisfied if you don't have light going directly into the black hole. It has to have some offset from the center. Using the substitution of u is the Schwarzschild radius over r, and differentiating both sides with respect to phi gives us a second order differential equation in u. We can immediately reproduce the stationary orbit of the photon sphere for a black hole by setting d squared u, presumably equilibrium, d phi to 0, and r equilibrium to the Schwarzschild radius over this u equilibrium, which is 3/2 Schwarzschild radius. Note the trivial equilibrium solution for u equals 0 at infinite distances from the black hole will not be discussed further. So they just set this equal to 0. Okay, I see. So stationary orbit means it's not speeding up or slowing down. Or, yeah, with respect to this phi component. So that's why I'm saying if we set this equation equal to 0, we'll get, we'll be able to solve for that stationary orbit. When you set this equal to 0, you get rid of one of the u's, and then you get that u is 3/2 rs. How about that? And he says, of course, there's a u equals 0 solution, but that would require little r to be infinity, which means you're like so far away from the black hole that it doesn't affect your geometry. You have a flat space-time. Okay, so simulated orbits. Given the differential equation 3, which was this guy, relating distance to the angular deflection can numerically integrate, relating distance to angular deflection, we can numerically integrate it using this Runge-Kutta formalism to figure 1. This is this. In this approach, we are propagating light from an observer to the black hole or to the background universe. This yields the same light path as the opposite direction because the solutions of 2 are independent to the direction that the light is traveling. Okay, so let's look at figure 1. Simulated rays of light satisfying equation 3 with delta 0 equal or less than 0 on the left and delta 0 greater than 0 on the right, with coloring indicating the magnitude of delta 0. Do we know what delta 0 is? Delta 0 is our initial perturbation. Okay, maybe we need to finish this paragraph first. Equation 3 requires 2 additional conditions. In Cartesian coordinates, we center the black hole at the origin, set the initial direction of light to be in the time direction. And the initial position, I'm not sure if this is time direction or x direction. The initial direction of light to be whatever this, and the initial position to be d0, b0 plus delta 0. b0 is the impact parameter. d0 can be arbitrarily large given b0 at a distance, which in the limit as d0 goes to infinity, b0 has to equal this random fraction of Schwarzschild radius, becomes the photon's capture radius commonly found in the literature. Delta 0 is our initial perturbation from which we use to avoid the ambiguity of defining the closest approach from light rays that spiral into the photon sphere. Importantly, d0 is interpretable as how far the observer is looking away from the rim of the optical black hole. Okay, so I think the setup that I see so far is I do think this is the time. It's saying you're moving in a time-like trajectory, which means that you're at rest with respect to the black hole. And the light has some initial position here, which is basically the important thing is this impact parameter, which is that, I guess they're saying this is that 3/2. No. Oh yeah, no, yeah, it is. So yeah, I'm not totally sure how to, because it seems like they're saying this B0 is again kind of the distance away from the center of the black hole that you need to be before you which will determine whether the light kind of falls in or it gets deflected. Earlier they said that that was 3/2 the Schwarzschild radius, but now they're saying it's somehow related to this time parameter. And the limit that it goes to infinity becomes root 27 RS. And also that this somehow, so this delta 0 is how far off you are from that critical point. So if D0 is a negative number, if it's just like small negative, then you're going to fall into the black hole. If delta 0 is a positive number, then you're going to get deflected. But somehow they're saying it's also interpretable as how far the observer, so something to do with the observer, which is different than the light, is looking away from the rim of the optical black hole. Interesting. Okay. The path for light with varying D0 can be seen in figure 1. All right, so we're looking at figure 1. Okay, so on the left side, they only drew trajectories that are have this delta 0 below. Delta 0 is negative, so you always fall into the black hole. So that's why you see all these trajectories that fall in. And I guess they're saying like if you're an observer standing here, I see. So they're saying where the light ends up way far away, is going to be a function of this delta 0. So for really, really negative values of delta 0, so this would be light coming in because it's not going to come out. But if you have really negative delta 0, you basically get absorbed right away. If you have only tiny bit negative delta 0, you will spin around a bunch of times. Or if not a bunch of times, at least once. Okay, so these are the only the trajectories where you fall in. On the right it's only the trajectories where you don't fall in. So if I send some light over here towards the black hole, it will kind of spin around and end up shot out some other direction. Okay. The black hole is shaded in gray with the last photon orbit indicated by that dotted line. Dotted gray line. That's this line. Each successive light trajectory plotted is a factor of 2 closer to the photon capture radius, with the resulting deflection angle increasing just below 40 degrees. Okay, so I guess they're saying that these are so they're saying that this color here indicates the size of d0, or this delta 0. But I'm not sure, like, this thing. So I don't see any orange coming in this initial bunch here. This looks like it's all purple. And I'm not sure if I'm supposed to get some orange and stuff at some point, but it looks like, no, these are all purple. But like, where does, like, this one's purple, this one's purple. It looks like we'd have these unique groups of like 4 or 5. It looks like 4 trajectories. Yeah, I'm not sure if these all actually come out of this like bunch here. I don't think so, because like, so purple is like this 10 to the 5, 10 to the minus 5. So it should be getting more blue as we go up and like as we go down. Yeah, okay. So these red ones and stuff, they're like, you just can't see them. They're right in here because this is B0. And so we're talking about really, really small values of delta 0 to get these red ones. Yeah, okay. So this picture makes sense. These are all the trajectories coming in, and they're saying that they plotted a bunch of lines here. They plotted a bunch of input distances here that are factors of 2 closer or further away from this B0 point. And you basically get, for each factor of 2, you get something like a 40%. So 40 degrees, like the difference between this angle here and this angle here is like 40 degrees, I guess is what they're saying. So as you scale d0 exponentially, e.g. by factors of 2, you get a linear scaling in phi. So that's what they mean by this last sentence. Logarithmic scaling towards the photon capture radius maps to linear evolution in phi. All right. Okay, So where were we? Speak on photon capture, found in literature. D0 is our initial perturbation, which we use to avoid the ambiguity of defining the closest approach for light rays that spiral within the photon sphere. Importantly, D0 is interpretable at how far the observer is looking away from the rim of the optical black hole. The path of light with varying D0 can be seen in figure 1. Positive and negative perturbations, respectively, spiral out into infinity or plunge into the event horizon as expected. As D0 becomes smaller, the deflection angle increases. Note that phi increases linearly when moving logarithmically closer to the photon capture radius. In figure 2, the results can be seen for positive, where the angle phi is the unwrapped deflection angle, and negative perturbations, with phi being defined as the angle orbited around the black hole at a time when the photon crosses the event horizon. For positive and negative perturbations. So when we have a positive perturbation in figure 2, phi is the unwrapped deflection angle. I assume unwrapped deflection angle just means the angle minus, whatever number of 360 you need, so that in case it orbited around more than once, it's only giving us the last bit of the angle, not with all the extra 360s. And with the negative one, phi is defined as the angle orbited around the black hole when it crosses the event horizon. For large perturbations, for instance, delta 0 is greater than 10 to the minus 2. The relationship between angle and distance is not simply exponential. However, small perturbations, a tight exponential relationship is visible. Okay, so let's just look at this plot here. Angle of rotation as a function of deviations from the equilibrium. In dimensionless units, distance over Schwarzschild radiuses. So in number of Schwarzschild radiuses. With phi equals 0, representing unbent light rays. For both small positive and negative perturbations, a clear exponential. So they're just saying that, like, this is a log plot on the x-axis and a linear plot in the phi. So when you have a straight line here, this is that they mean that phi is D0 is phi to some exponential, I guess, right? Or some exponential to phi, yeah, something like that. That's what this thing says. So they're just trying to say, before we get up to like this point over here, you see this is a straight line. So that means that phi to some e to some power of phi with some constants and stuff around there is going to be the function that delta fits until you get out to like here where you see this like bending and you don't have a line anymore. So you have some different kind of functional relationship there. To determine the exponential in the exponential regime, we can fit phi as s ln delta 0 plus c. And we see that the slope turns out to be about -1. Inverting this expression for d0 implies that in order to achieve orbit of f, so they're saying that right, so if we want to achieve an orbit, we need phi to be pi. That would be one orbit, or 2 pi, sorry. So they're just saying if I plug 2 pi into here, then delta 0 is e to the minus 2 pi s, basically. or sorry, if I plug a delta phi, so the change in d0 to get a change in phi of 2 pi is given by this, minus 2 pi s. So that means we would need to be 535 times closer to the optical edge to get 1 extra rotation. Or 535 more. Damn, is that the scale that we're talking about here? Does it show? I don't understand these numbers really because e to the minus 2 pi is not 500, first of all, if s is minus 1. Or whatever, e to the 2 pi is not 500. But I'm just going to assume there's some sort of unit transformation they're doing here that I'm not understanding. But roughly, you know, they're saying that you can find some factor here that tells you using the fit that you made here, you can see how much closer you have to be to the how much you have to move in this y space here to give you another orbit around the black hole. But this only holds for, like I said, really small delta zero anyway. So this whole relationship only really holds like in this little bit of space here. Like it doesn't hold out here. In fact, it only holds, what do they say, 10 to the minus 2. So 10 to the minus 2 means, you know, 1/100th of a Schwarzschild radius. So 100th of this radius away from this B0. So saying you get 535 here would mean that this entire model doesn't work because you have to be within 100th of the black hole for this model to work. So that's why I'm saying I'm sure there's something that I'm missing here, but that's the basic idea of what they're trying to get across in this section. All right, so on to linear stability. Let's see what we got here. Work-wise, a little bit still, 7 pages. Okay, I'm gonna go for maybe another 10 minutes and then maybe we'll come back to this tomorrow. To interpret these numerical results, we will utilize linear stability analysis by adding small perturbations, u going to the equilibrium u plus some delta, to the equilibrium solutions of 3. Okay, so they're just going to replace u by some equilibrium value plus a small parameter, and then set the derivatives of the equilibrium value to 0, and just rewrite this equation in terms of just the small parameter. Sorry, they're setting the equilibrium to 2/3, but the derivative of 2/3 is of course 0. So they say you basically get squared here. Okay, just some algebra. So you end up with this equation, and they're just going to approximate this as delta, because delta is really small. So they're throwing away delta squared terms. And they say you get this equation, which does look like the formula they had before, right here. Evidently, the first term grows in magnitude while the latter decreases, with constants delta 1 and delta minus 1, determining in which regime each term dominates. The constants are set by initial conditions of the trajectory, which will be discussed further in linear stability. Note that the dual exponential form is to be expected, as the equilibrium solution is a saddle point. An alternative perspective on these exponential solutions is in the phase space of equation 3. This shows in figure 3, where for every initial condition, u and du dphi, a vector is plotted indicating the angular change in both variables, i.e. du dphi and d squared u dphi squared, shown in figure 3. Figure 3, entire left and zoomed in phase space for light trajectories obeying equation 3. With arrows coloring indicating the magnitude of the change. Brighter hues are longer vectors. U equals 1 is the event horizon. U equals 0 represents infinity. And U is 2/3 is the photon sphere. If we're at the photon sphere and at a stationary orbit, or in du dphi equals 0, you're on a stationary orbit. Notable, this is not a stable fixed point, as deviations will grow. Stable and unstable manifolds are drawn in the enlarged version, which are approximately linear. A cross-stable manifold evidently represents a separatrix between the initial conditions of the trajectory, which will cross the event horizon or be ejected out to infinity. Thus, the stable manifold is equivalent to the optical rim of the black hole. I'm really not sure what they mean by stable and unstable manifolds here. Seems like all of this, if there's only one radius where where you can get these circular orbits, then everything's not stable. So maybe we need to read some more of this again so that they define what these things mean. For every initial condition, u du d phi is a vector plotted indicating the angular change in both variables du d phi and d squared d phi squared. D squared du d phi squared. So u again was this unitless thing, right? Unitless distance from the number of, or sorry, 1 over the number of radiuses away that you are. So here they have the space of u and du d phi. Not sure why they do du d phi instead of just phi. But they're saying trajectory is terminating at u equals 1. Reach the event horizon while u equals infinity is. So, okay, let's look at some of these trajectories. So, like, this trajectory, high du d phi. So that's high angular momentum, I guess. And you're really far away. Or sorry, you're at infinity with a really high angular momentum. These arrows indicate that you go into the black hole. That doesn't make any sense. So one thing they're saying is if you're right here, you stay there because you have no angular momentum and you're on the photon sphere. Which I buy. Set of initial conditions which converge towards the photon sphere, called the stable manifold, is indicated with the blue line. Okay, so you have to be somewhere on this blue line to end up in orbit. So yeah, I don't totally understand what the difference between the unstable manifold is. It seems like you reach the fixed point, but with phi equals minus infinity. So that means you get there after going around infinitely many times, but they also said that, well, I'm sorry, I'm hitting this too much. But they also said the other one, you only get there asymptotically as well. Photons on the trajectory will asymptotically approach the photon sphere. So asymptotically means it takes forever. Conversely, in the unstable manifold, you get there, but it takes forever. All right. Symmetry between stable and unstable manifolds is seen in the phase space due to Schwarzschild metric, and therefore equation 14 being independent in the direction of time. All right. So yeah, I think it's been about the hour. That was what I was planning to do here. So I'll try to come back to this again tomorrow night. We'll see if we can finish up, get through what amount of the paper we can. Until then, appreciate it if you're watching, and have a good night.